Hi, my name is Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know for the Regents on formulas and equations. Now, the first thing you need to know when we're dealing with formulas and equations is a chemical formula. Well, I have one up here right now. This represents a chemical formula. You see 2 hydrogens plus 1 oxygen produces 2 waters. Now, all chemical formulas and all chemical symbols show 2 types of information: what you have and how much you have. Now, what you have is sometimes called qualitative information, and how much you have is sometimes called quantitative. So what's the qualitative information? What do you have? Well, you know here you have hydrogen. That's what you have. What do you have here? You have oxygen. That's what you have. And what do you have here? You have water. That's the qualitative information. What's the quantitative information? Well, it's how much you have. Well, I have 2 hydrogens here. I have 1 oxygen here. And I have 2 waters here. That's the quantitative information. But notice, I have 2 hydrogens, but I really have more than 2 hydrogens because each hydrogen has 2 hydrogens, so it's really 4 hydrogens. Okay, I know I'm going a little ahead of myself, but we'll get there in a second, I promise. You need to understand certain pieces of this chemical formula to understand what I was just talking about. First of all, you need to know what a coefficient is. This is a coefficient. It's the number before the symbol, the big number. And the coefficient represents the moles you have. Now, you're thinking moles, oh, I remember moles. Now, go to the mole concept if you need further clarification on what a mole is, and we'll talk more about that in another lesson. But for right now, moles just mean how much of something you have. And if I have hydrogen, I have 2 moles of hydrogen. Here I have oxygen. Notice there's no coefficient here. That doesn't mean I have no oxygens. When there's no coefficient, that means 1, because I don't have to put it, because it's understood. So I have 1 mole of oxygen, and I have 2 moles of H2O, which is water. Those are the coefficients. You need to understand them. The subscripts are these. They're the little numbers, and they represent the number of atoms. Now, what an atom is the smallest part of an element that has all the properties of the element. So this is an atom. This has 2 atoms of hydrogen. So there's 2 specific hydrogen atoms here. There's how many atoms of oxygen? Well, there's the subscripts 2. So there are 2 oxygen atoms. How many hydrogen atoms do I have here? Well, it's H2O. This represents for the H. So there's 2 H atoms. And then same deal with coefficients. If I have nothing here, that means 1. So I have 1 oxygen atom here. So the subscripts tell me how many atoms I have, where the coefficient tells me how many molecules or moles I have of a given molecule. And this also tells me moles, but it tells me moles of atoms. So here I have 2 moles of hydrogen atoms. Moles just represent an amount. Now, the next thing you need to understand, and you hear these terms all the time, and a lot of teachers take for granted that you know what this is, but a Regents tutor, we want to make sure you know everything, and we don't want to take anything for granted. So we're going to tell you what the difference between a reactant and a product is. And you may be thinking it's simple, and you may be thinking, oh, thank God, somebody's finally telling me what this is. A reactant is what you start off with. Everything you have in the beginning of a reaction is a reactant. So in this case, the reactant is the hydrogen and the oxygen, separated by the equal sign, the arrow, excuse me. The reactants are what you start off with. They form products, what you end up with. Well, what are the products here? The products here is the water. There's 1 product here. There happens to be 2 waters, but there's only 1 specific type of product. Products are what you end up with. Now, what does this arrow represent? You see this all the time. The arrow represents the term produces or yields. So what this is saying is 2 hydrogen molecules plus 1 oxygen molecule produces or yields 2 water molecules. That's a chemical equation, and you need to understand it. And this is a full chemical equation. The next thing we need to talk about after we understand the chemical equation, and I'm going to leave this equation up here because it will play a purpose later on, but you need to understand the difference between a chemical and a physical property, or a chemical and a physical change. Let's talk about chemical and physical changes first. A physical change is a change in a substance that does not form a new substance. For example, let's say I have water here. This is water. It's H2O. I have my water right here. Let's say I took this water and I decided to heat it. And it started to bubble and it started to boil, and then I started to produce gas vapor and liquid and vapor. So now the water was turning into the gas, right? The liquid was turning into gas, into steam. Well, is it still water? Is it still H2O? Of course it is. If it's still H2O, then that's a physical change. It's changing. It's just changing the phase from liquid to gas. That's a physical change. If I drop salt in water and it dissolves, and I mix it around, and now I don't see the salt anymore. But remember, it's still salt and water. I still have those two things. Therefore, that's a physical change. Physical changes is when you do not produce a new substance. Well, you guessed it. What do you think a chemical change is? A chemical change is when you produce a new substance. For example, in my equation here, I take hydrogen and oxygen, and I produce water. But wait a minute, it's the same thing, right? Water is hydrogen and oxygen. No, it's a totally different substance. Water is totally different than hydrogen and oxygen. And how do you know that? Well, if you want to light a fire, if you want to light a match, you need oxygen there, right? In order to light a fire, you need some oxygen. Hydrogen gas is very explosive. It reacts completely and it will blow up and cause a fire. Hydrogen's explosive and reactive. Oxygen's needed to start a fire. Two properties. What happens when you mix them together? You produce water. What happens when there is a fire? What do you put on a fire? You put on fire water. So obviously, the properties that hydrogen's flammable and oxygen is needed to start a fire, and water is used to put out fires, means you produce something totally different, and you did, because it underwent a chemical change, because you produced a new, different substance. Anytime you produce a new substance, it's a chemical change. Anytime it's the same substance in a different form, it's a physical change. Now, how about chemical and physical properties? Well, chemical properties are properties related to how it behaves during a chemical reaction. So, for example, copper burns in the presence of oxygen or whatever. That's a chemical property. Iron rusts. That's a chemical property because it's forming a new substance. So, another metal, chromium, corrodes. Again, corrosion would be a chemical property because it's dealing with it during a chemical reaction. A physical property is the same thing as we talked about physical change. A physical property is a property related to when it doesn't change, it's just changing a phase. Density is a physical property. Conductivity, how well it conducts electricity, is a physical property because it's still the substance. The only time it's a chemical property is when the substance changes. So that's the difference between a physical and a chemical property and a physical and chemical change. The next thing I need to talk about is something called a diatomic molecule. There are certain molecules, there are certain atoms that can never be found alone in nature because they're too reactive. So what happens is they generally bond to themselves, and they're called diatomic molecules. Di, atomic, or atomic atoms, two atoms making up a molecule. Now, you just need to understand that certain substances can never be found alone in nature. For example, here I have oxygen, but for each molecule of oxygen, how many atoms do I have? There are two. So this is an atom, this is an oxygen molecule, but it's a diatomic molecule because there are two oxygens. Same with hydrogen. It's a diatomic molecule because there's two hydrogens. Notice that here, oxygen doesn't have to have two. Why? Because now it's bonded with something. It only has to have two and be a diatomic molecule when it's bonded to itself or when it's alone. Well, it's not alone because it has to be bonded to itself. You have to know which atoms form diatomic molecules. And you just need to know Brinkelhoff. Yeah, Brinkelhoff. That's right, Brinkelhoff. I know it sounds weird, but Brinkelhoff. That just tells you which atoms are diatomic molecules. Brinkelhoff. Br, bromine. I, iodine. N, nitrogen. Cl, chlorine. H, hydrogen. O, oxygen. And F, fluorine. Brinkelhoff. If you know Brinkelhoff, even though it sounds stupid, it will help you understand what the diatomic molecules are. And now we're done with that because you know Brinkelhoff, so I don't even have to talk anymore. The next thing you need to know is table E. Table E is very, very, very important. Table E shows polyatomic ions. Most of the time, when you have different atoms bonded together, they form a neutral compound, which means there's no charge. But sometimes, there are certain substances that, when bonded together, have an actual charge. For example, if you look on table E, phosphate is a polyatomic ion. It's PO4 with a 3- charge. That's the phosphate ion. And all the substances on table E represent substances that bond together that form a charge. And you just have to be familiar with the polyatomic ions, and you'll see why later. Let's say we want to just take a substance like calcium phosphate. Calcium phosphate, and I'd ask you, how many atoms are there of each element in calcium phosphate? Now, why is it hard? Well, because you have this whole thing that's PO4, but then there are 2 of them. Calcium's easy. How many moles of calcium atoms do you have? You have 3. Why? Because there's a 3 here. The subscript's 3, and that tells you how many atoms you have. Now let's do, well, how many total polyatomic ions, how many total phosphate ions do you have? 2, because it says it right here. But we're talking specifically about phosphorus and oxygen. Well, if you have parentheses and there's a subscript outside, it goes to both of them inside. So how many total phosphorus do you have? You have 2 P's. 2 P's. How many total oxygens do you have? Well, you have 4 in each phosphate. There's 4 oxygens, but there are 2 phosphates. So 4 times 2 is 8. So here you have 8 oxygens. So you need to understand how to tell how many atoms of a given element you have, especially when you're dealing with polyatomic ions, and sometimes that gets tricky because of the parentheses. And you'll see that later on, and we'll talk more about that later on. Okay, the next thing we need to talk about is different types of formulas. Well, you can have a structural formula, which tells you what it looks like, but we're going to talk about that more later on in a different lesson. You can go to the concept on structural formulas, but we're predominantly dealing with the difference between a molecular formula and an empirical formula. Molecular formula and an empirical formula. Molecular formula is the actual formula, the formula that you actually have. For example, let's say you had C2H4. You had 2 carbon atoms and 4 hydrogen atoms bonded together. This is your molecular formula because that's what you actually have. The empirical formula represents the simplest ratio. Well, what's the ratio of 2 to 4? Well, the ratio here is 2 to 4. But if you made an empirical, you would simplify it. Well, you can simplify this because what you do to turn a molecular formula into an empirical formula is you divide by the greatest common denominator, the greatest common factor. What is that? Well, in 2 and 4, it's 2. So you divide both by 2, and the empirical formula then becomes CH2, because 1 and 2. So this is the empirical formula, because this is the simplest ratio, 1 to 2. This is the molecular formula, because that's the actual ratio, 2 to 4. Molecular is what you have. Empirical is the simplest form. And you need to understand empirical and molecular formulas. Okay. Now we're going to talk about writing formulas. Sometimes people have problems with writing formulas, but it's actually pretty simple. Writing formulas can be easy as long as you know the rules to how to write formulas. Well, the first thing you have to do is, let's say, and I'm going to erase this now. Let's say we want to write the formula for something like calcium chloride. It doesn't matter what it is. Calcium chloride. Now, first thing you have to remember is whenever you're writing a substance, the positive comes first, the negative ion always comes second. So here, you know that the calcium is positive and the chlorine is second. So you write the 2 formulas. Now, what do you do with those formulas? Well, first you have to find the charges. And you go to the periodic table, because it says on the periodic table, you could see on the periodic table, it says selected oxidation states. Now, that just is another word for now for charge. So here, calcium has a selected oxidation state, as you can see on the periodic table, of +2, which means the charge of calcium is +2. Chlorine has many different oxidation states or charges, but when it's negative, you always take the highest negative one. So chlorine only has one negative ion, negative charge. It's -1. So that's what it is, -1, because we know chlorine's negative because it's second. Now, the way we write formulas is we use something called the crisscross method. The crisscross method is when we take just the number, not the charge, just the number up here, and we crisscross to make the formula. So this 2 comes down here, and this 1 comes down here. But remember, we don't have to write 1. So the formula now becomes, instead of CaCl, it becomes CaCl2, because you crisscross the numbers. That's how you write formulas. It's very simple. You take the charge that you have from the periodic table, and you crisscross them, and that becomes your charge. One thing to keep in mind that's very important is it must be ionic. It must be empirical. So here you have empirical formula, CaCl2. Let me just do one that's not ionic just to give you an idea of what I'm talking about. That's not empirical, and then you have to convert it to empirical. Let's say I want to draw the formula, and let's just use calcium here because we're still using it. For calcium oxide, well, calcium's +2, because we just found that out. Oxygen is -2, because it says that on the periodic table. -2. Well, we crisscross and we get Ca2O2. But remember, I said it has to be empirical. This is not empirical. You can reduce 2 and 2 to 1 and 1. So this formula would be CaO. So when you're writing formulas, you just have to make sure you remember that the empirical formula is the formula you need to do. And let me just do one more with polyatomic ions, only because polyatomic ions tend to confuse some students, and we want to make sure that you're never confused. Okay, let's say we're talking about calcium phosphate. Well, you know from table E that phosphate is PO4. Now, this is the easiest kind of substances because, well, calcium we know is +2 again. What's the charge of phosphate? Well, it says it right on table E, 3- or -3. So we put that right there. So now we have calcium with +2, phosphate with a -3. The trick with polyatomic ions is the parentheses. Because remember, if you're going to put a 2 down here and a 3 down here, you need to have the 2 in front of the whole phosphate. And they would try to trick you. The answer here would be Ca3PO4. And all I got to say is make sure that you put the parentheses around the PO4. But it's still simple formula writing. There's nothing tricky about it. It's just crisscrossing and turning it into empirical if you have to. Calcium phosphate looks like that. Make sure you don't forget the parentheses when you're dealing with polyatomic ions. All right. Now you know how to write formulas. Next thing is naming. Naming could be a little tricky. It could be a little easy depending on who you are and what you know, but you need to understand naming. Naming using, and we call it the IUPAC system of nomenclature. That's just what chemists use to name them. Don't worry about when you see IUPAC. It just means that's the name that you need to worry about, the naming system. Before we go over naming, I got to tell you a quick difference between ionic and covalent bonds. You can go to the concept on them and learn a lot more about them. But for right now, ionic and covalent bonded substances are named differently. So I have to explain to you the difference quickly. First, the major thing you need to know is ionic is between a metal and a nonmetal. And a covalent is between two nonmetals. And that's it. So if you understand that when you're dealing with a metal and a nonmetal, or, a polyatomic ion, you're dealing with ionic bonding. When you're dealing with nonmetals, only two nonmetals, you're dealing with covalent bonding. and that will help us. So let's first talk about binary ionic substances, which is just, binary means two. It's just a metal and a nonmetal. And the way you name it is very simple. Well, let's say you have calcium CaCl2. This is what you do. The first substance always keeps its name. And how do you know the name of these substances? On table S, they list every element and every name you need to know. So you see on table S, Ca is calcium. Cl is chlorine. The way you name it is Ca. The first element always keeps its name. So Ca is calcium. This substance will be calcium something. So you know you're going to be dealing with calcium. The second substance, the negative substance, remember it's always positive then first, then negative second. The negative substance always ends in ide, I-D-E. So this is not calcium chlorine, it's calcium chloride. This is calcium, this E looks weird, let me just change it. Calcium chloride, because it ends in ide. Notice you did not do anything with the number here. There's a 2 there, and you didn't do anything with it, because you don't have to number it, and you don't have to show the number. It's just calcium chloride. And that's how you name binary ionic substances. If it was Al2O3, doesn't matter the numbers, it would be aluminum oxide. It's all the same thing. Binary ionic substances, metal and nonmetal, you name it like that. Positive, then negative, and then the first one keeps its name, and the second one ends in ide. When polyatomic ions are involved, things get a little different. And those are other types of ionic substances. When polyatomic ions are involved, what you need to know is it's the same rules. Positive first, negative second. But the polyatomic ion never changes its name. So when you had CaPO4, Ca3PO42, this substance would be called calcium, because the first one keeps its name, phosphate, because you don't add it doesn't end in ide. That's how you tell the difference between this and this. This is calcium phosphate, while this, since it's P, ends in ide, is calcium phosphide. And if it's first, obviously everything keeps its name. So if it's like NH4Cl, NH4, as you can tell on table E, is ammonium, and Cl ends in ide because it's the second element. This is ammonium chloride. And that's how you name other types of ionic substances, and other meaning when there's a polyatomic ion involved. Just make sure you know polyatomic ions always keep their name. The next thing we have to talk about is naming covalent substances. And a covalent substance, as you remember, 2 nonmetals. And when you're naming covalent substances, there's one extra step. You have to tell me how many atoms there are of each. For example, if I have N2O5, well, that's covalent because nitrogen is a nonmetal and oxygen is a nonmetal. So those are 2 nonmetals, so you know it's covalent. You need to know the prefixes for each of them. 1, and you can see on the slide window, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. You need to remember those. And it's very simple, though. The same rules apply. First one keeps its name, second one ends in ide, except you have to just put the prefix before them. So there's 2 nitrogens, so 2 is dinitrogen. 5 is pentaoxide, except when you're naming something that starts with a vowel, you drop the ending of the prefix. So instead of pentaoxide, we just say dinitrogen pentoxide. But it's very simple. First one keeps its name, second one ends in ide, and you just got to put the prefix there. And the only other exception there is when the second substance, the second element, has only one, the first one has only one. So here you have CO2. Now that's 2 nonmetals. Why wouldn't you say monocarbon dioxide? We call it carbon dioxide. Why? Because when the first element has 1 atom, you don't have to say mono. You only have to say it for the second one. So this would be carbon dioxide. And if it was CO, this one would be carbon monoxide. Carbon monoxide. And that's the whole thing. And that's how you name binary covalent compounds, because that's all you need to worry about. The next thing we need to talk about is the stock system. The stock system confuses a lot of students. A lot of students get very confused with the stock system, and it's really very simple. And the problem here is, what happens when you get an element that has more than one positive charge or positive oxidation state? Well, I told you that if there's more than one negative, you take the top number. But for positives, you can't do that. For positives, you cannot just take the top number. You need to be told what the charge is. For example, if I wanted to draw iron oxide, well, we know how to write formulas. Very easy, right? Fe is iron. Again, table S if you don't know. O is oxygen. Well, let's see. Fe, we go to the reference table, and we see that iron, Fe, has two positive oxidation states. So we cannot just pick the top one. So we can't do this. We have to know what the charge is. And the way we designate it in the formula, in the naming, is we put a Roman numeral. Iron 3 oxide, iron 3 oxide, just means that iron's oxidation state is +3. Oxygen's oxidation state, well, we know from the periodic table, is -2. But we don't even have to go to the periodic table for iron. We know that it's iron +3 because the Roman numeral here. You just need to know that Roman numerals tell you the positive oxidation states. And then you could draw the formula because you do the crisscross. And you get Fe2O3. And that's the formula for iron 3 oxide. Very important you understand the stock system. Know that the 3 does not represent iron's subscript. Because notice iron's subscript here is 2. The 3 up here represents the charge or the oxidation state of iron. Very important that you know what the Roman numeral represents, because you will be guaranteed to get one of these questions on your Regents, and if you know what the Roman numeral means, you'll get it right. Because all you do is you know that it means the positive oxidation state, and you crisscross, and you get your answer. And note that the Roman numerals only deal with positive oxidation states. So whenever you see a Roman numeral, you know you're dealing with the positive charge or the positive oxidation state. Okay. Now the last thing we need to talk about, well, one of the last things is the type of reactions. The type of reactions that we're talking about, there are 4 major types of reactions we need to talk about. They're synthesis, decomposition, single replacement, and double replacement. For synthesis, it's very simple. You're making something. So with synthesis, you're actually making something. The general formula for synthesis is A, you're starting with A, and B, A plus B, yields C. You're taking 2 small things, putting it together, and making it bigger. A real-life example to that is taking 2 hydrogen plus oxygen and getting water. So that is synthesis. Hydrogen plus oxygen produces water. You start with small things, you join them together, you make them bigger. That's synthesis. Decomposition is the exact opposite of synthesis. You're taking something and you're decomposing it or breaking it down. So it's C gets broken down into A plus B. Or a real-life example would be water would get broken down into hydrogen and oxygen. So that is decomposition, when you're breaking something down. And you'd be able to see different types of decomposition reactions. The next one is single replacement. Now, I have to draw that one here. Single replacement, well, the general formula is A plus BC produces B plus AC. And notice you have an element and a compound producing an element and a compound. And you have to see what happens here. What happens in this equation is single replacement. The element replaces one of the parts of the compound. So A replaces B, and now B is gone. because everybody wants to be bonded together, but only the best and most active substances will actually get bonded. And I'm going to give a real-life example to show you what I mean here. Let's say we take zinc plus copper chloride. And you want to know what's produced. Well, you have to, in order to do a single replacement reaction, you have to know if zinc, for example, the metal zinc, will replace the metal copper. Will zinc replace copper? Who knows? Well, you do. How do you know? From table J. As you can see on the slide window, table J shows the activity series of different metals. Now, if everybody wants to be bonded together, copper right now is very happy because copper is bonded together. Zinc is unhappy because it's not bonded together. So zinc wants to be bonded together. So it's going to try to kick copper out. Now, will it do it? Well, let's look at table J. Who do you think is going to win in a fight between zinc and copper? The one that's more active or the one that's less active? Obviously, the one that's more active. So if you look on table J, zinc is higher on table J than copper, which means zinc is more active than copper, which means zinc will kick copper out and join where it was. So now copper is going to be alone, and zinc is going to be in place where copper was. So this represents the single replacement reaction. Now what if, just one more, what if I had copper plus zinc chloride? Well, we just learned that zinc's above copper. Will copper be able to replace zinc? No. So in this case, since copper wants to replace zinc, but zinc won't let it because zinc's more active, what's the reaction? There is no reaction. No reaction. This does not happen because copper is not above zinc. Very important that you understand that here. Now this is bonded together. This is not. If the metal has to be above it in order to replace it. Very important that you understand that for single replacement reactions. And the last type of reaction is called a double replacement reaction. And a double replacement reaction has the general formula AB plus CD yields AD plus CB. Now, notice here, compound plus compound yields compound plus compound. So it's very easy to recognize a double replacement reaction. You have two compounds on each side. Compound, 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 compound. Now, the most important thing you can learn about a double replacement reaction is understanding the charge. Remember, positive always comes first, negative always comes second. So this is positive, this is negative, and this is negative. Now, in a double replacement reaction, it's very easy to get the products. Why? The positive of one always bonds with the negative of the other. And the same thing, positive, negative, positive, negative. Now, so you have AD, which is positive, negative. But why do you have CB and not BC? Because remember, positives come first, and C was positive. So it's positive, negative. And that's double replacement. Let me give you one example of a double replacement reaction. Let's say I had KNO3, which is part of a polyatomic ion, plus NaCl. Well, we know K is plus 1, NO3 is negative 1, Na is positive, Cl is negative. So what are the products? Well, positive, negative. K goes with Cl, and Na goes with NO3. Which comes first? Na is positive, NO3 is negative. NaNO3. This is your full double replacement reaction. Just keep in mind, positive goes with negative, and positive comes first, negative comes second. And that's a double replacement reaction. Now, you just learned about all the different types of reactions. It's very easy to know how the different types of reactions, right? Synthesis is building something up. Decomposition is breaking it down. Single replacement, an element in a compound gives you an element in a compound. And double replacement is two compounds together yields two more compounds. The last thing we have to do is balancing chemical equations. And balancing chemical equations just makes sure that the number of atoms on each side of the equation are equal. For example, let's say we took aluminum plus oxygen. Remember, oxygen is a Brinkelhoff, a diatomic molecule, produces, and you know how to write the formula for aluminum oxide, Al2O3. In any equation, the total number of atoms on one side in the reactants have to equal the total number of atoms on the right side. That's called the law of conservation of mass, or law of conservation of matter. And all that means is matter or mass cannot be created or destroyed. Can't be created or destroyed. So whatever you start with, you have to end up with. Now, to balance an equation, you have to make sure they're all equal. And the way you do that, you can't change the subscripts. The only way you can make sure they're equal is by changing the coefficients. So this is how you do it. You separate the products from the reactants, okay, and you put down how many you have of each. Al, aluminum, there's 1 here. Oxygen, there's 2 here. Aluminum here, there's 2. And oxygen here, there's 3. Are they balanced? Of course not, because we don't have the same numbers. So let's first, there's 2 aluminums here. Let's make 2 aluminums here by putting the coefficient 2 there. So now we change this to 2. Now, oxygen is not balanced. There's 3 here and 2 here. We can't put any one number there that will make it work. So what we have to do is, if we put a 2 here, this makes it 4. Well, what if we put a 3 here? That will make it 6. And then a 2 here, that will make it 6. You've got to find the lowest multiple. So that's 6. So if we put a 2 here and a 3 here, this becomes 6. This becomes 6. But we're not done because the aluminum is now 4. But the aluminum's only 2 here. We just got to change this. And we could erase once we already did it. And now we have this. And this represents a full balanced equation. Just keeping in mind that the total number of atoms on one side is equal to the total number of atoms on the other side. This is a full balanced equation. And if you do it the Regents-Tutor method by separating reactants from products, you'll never get a question wrong. And you just have to know that all chemical reactions show a law of conservation of mass and matter. Mass and matter can't be created or destroyed. But they also show a law of conservation of charge and energy. All chemical reactions show a conservation, which means they can't be created or destroyed, of mass, matter, charge, and energy. And you can go to the concepts on these and learn more about them, but that's what you need to know, and that's what a balanced equation shows. So I hope you learned a lot about formulas and equations. It was a lot of information. I think you learned a lot. Just to be sure, after you do this lesson, go to all the questions that relate to formulas and equations. After you do each question, make sure you listen to the video explanation, even if you got the question right, but especially if you got it wrong. Listen to the video explanations. The more you do this, the more repetitive it becomes, the more it sticks in your head, and the better you will be at the Regents. Make sure you come to chats if you have any questions. Look over the review sheets. Go over the lessons again. But I think you're in good shape. I hope you learned a lot.